Okay. Some announcements before we start. Okay. So those announcements would be your homework. One is due at 5 p.m. today, FYI. I know this is like the third, if not maybe nth time you've heard this, but I want to help you out. It's due at 5. There is one more office hours session with the person doing it today is Brian, although Tony was this morning. So you have 2 office hours before it's due, although one already passed because one was in at 8 a.m. All right, so if you have any additional questions, please show up or send your TA an email. You can also send us an email. My Fridays are kind of booked with meetings, so I may not see it. So best to post to the discussion forum or your TA, and you can CC me if you wish, and I would try to get to it if I see it. Some of you have already been emailing, posting to the discussion forum, bringing up questions and recitations, so thank you for doing that. We've tried to share the answers as best we can if it pertains to the homework, and of course that way everybody has the same answer and we're all on the same page. With that, I did come across a question from a student regarding the number of atoms in a hexagonal closed pack unit cell and the volume that is associated with that unit cell. We didn't discuss it in great detail, you know, deriving the volume and such. That has already been derived for you in your book, and that's given in equation 3.7b. Now, the unit cell that is used to derive that volume is shown in the example, and they use the hexagon, the hexagonal prism, right? And so we discussed that there are 6 atoms within that unit cell, and if you choose to go with the parallelepiped, the volume would be 1/3 of that, and the number of atoms within that unit cell would be 1/3, which is 2. So we covered that. So as long as you use the correct number of atoms for HCP, depending on the convention that you used, your volume should be equivalent to that, right? So don't mix the atoms and the volumes is all I'm saying, right? So I wanted to clarify that in case there was any confusion. How many atoms per unit cell do I use if this is the volume of the unit cell? Okay, just keep track of which cell you use. It should be equivalent, and if you haven't already tried it yourself and verify that indeed you get the same you get the same density. Okay, and of course Martin Luther King Jr. Day is on Friday. There will not be a class lecture that day. All right, any other questions or anything housekeeping that I missed before we continue on and finish up Module 3, crystal structures and crystal systems? Yes? I'm sorry? Ah, yes, okay. I'll switch back, mainly because there's a request. But I will switch back quickly enough. Okay, anything else? How was recitation for the first week? A nod of approval. Okay. I know some of you, because you're in different sections, some of you have had different formats where you just had the worksheet, and some of you may have had the worksheet via top hat questions. You're welcome to let us know which one you prefer. Politely. Tell us politely and kindly. Offer your constructive criticism. Okay. 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 Let us. All right. Actually, I just want to recap because, you know, with the time in between, there's always some memory loss, let's just say. So let's jog our memory. We worked on figuring out the coordinates within a unit cell. So the example we left off was the coordinates of 1/2, 1, 1/2. And the other points in this particular unit cell, this prism here, the points are denoted 1 through 9, and the points QRS are worked out for you. What you'll notice is that there aren't any commas, nor are there parentheses, square brackets, angle brackets, or anything like that. You just put the 3 numbers together, and it could be and it is fractional, right? Because you want it to be within the unit cell. Because what we talked about in terms of crystal symmetry is that sorry. Okay. What we talked about in terms of crystal symmetry is that it's periodic. You can translate in all three directions, and thus the origin of your unit cell is arbitrary. You should be able to shift it in any which way, right? Because you as a human, when you look at your material, you can change your frame of reference however you like, right? And then if you have an instrument that's going to detect whatever property of that material, unless you know the alignment in some sort of way because you've done a calibration, it's also arbitrary. Your frame of reference will always be changing, and thus mathematically, your point of origin is arbitrary and thus can be translated. So we define the unit cell as the unit, right? So length of 1. So vectors A, B, C, length of 1. Then we want to confine everything, the symmetry that we talk about within that unit cell. So it's all fractions, okay? You may have also come across the coordinate system because I've had 2 questions already, but the Google says, okay, the article wasn't in there, but Google says this: you must read the convention and the context within that information is discussed, okay? So you might have seen parentheses, you know, A, comma, B, comma, C, or whatever this point is, right? It could be Q, comma, R, comma, S with parentheses. You could have seen that as well. And now some people do refer to it as that, but I want to be consistent. Your book chooses, and it is also convention, it's a primary convention, that the coordinates is just QRS, no commas, no parentheses, no anything, just 3 numbers put together. Okay, so we're going to agree to go with that convention, and that's how we're going to proceed. So if I get an email, but the Google says, there's my answer for you, okay? That's the context behind that. Okay. Okay. So now we're going to continue on with crystal direction as well as crystal planes and how that is used to navigate throughout the 7 different crystal systems and the 14 Bravais lattices. Okay. Oh, actually, sorry, I must go back one moment. Yes. Okay. So we talked about some very special, highly symmetric systems, such as the cubic system, FCC, BCC, simple cubic. We talked about hexagonal, and so that's another crystal system. But there are others. In fact, there are 5 others. And so when we talk about the lattice parameters, right, for the cubic system, we said that all the sides are the same. So all the lattice parameters, A, B, C, they're all the same because they're all just A, because all the sides are the same. Now, what happens when one of the sides is not the same? Well, we saw that already in hexagonal, right? In your basal plane, you have A is equal to B, but that's not equal to C. Okay. Well, what happens if the angles are 90 degrees all throughout your unit cell? That looks like cubic, but one of the sides is not the same. That could be tetragonal, so A is equal to B. So here, this could be B, but it's the same as A. So A is equal to B, but not equal to C because C is a little bit longer. Okay? But the angles are all 90 degrees. And so we define the angles as alpha, beta, gamma. And then you can go on and say, okay, well, what if A is equal to B is equal to C, but the angles are not 90 degrees? And so you can see here there are different versions of different unit cells. The main ones that we'll be talking about are just cubic and hexagonal. If you take advanced crystallography, you will have your chance to discuss all 7 crystal structures. And if you're an MSc, your next course on structural materials will go into all of this. And if you're not an MSc, you can still take it and learn all about the 7 crystal structures. But for this class, we're going to focus on cubic and hexagonal system. Okay. And then there's orthorhombic, monoclinic, triclinic, and all that. So you lose symmetry as you go on. Okay, so that's that. Now, where the atoms go, where your base, what your bases entails, we've seen there are differences even within the crystal system. So here's simple cubic, here's BCC, here's FCC. The same thing for tetragonal, right? A is equal to B, but not equal to C. Well, you can put all the atoms at the corner, very similar to simple cubic, right? Just put the atoms at the corner. But then body-centered tetragonal, you can put one atom at the body center, very similarly to what we've done with body-centered cubic, That changes the symmetry, and now that's called body-centered tetragonal. And then if you iterate that, let's say we put atoms at the faces. We can also put atoms at the faces, let's say there, and that's called base-centered orthorhombic, and so on and so forth, okay? And here you put more atoms at the faces. So that results from the 7 crystal systems, you now can get 14 crystal or Bravais lattices. And then from all these permutations, you can end up with what's called 230 space groups, and that defines all the symmetries that we know of. Okay. Do I expect you to have memorized like every single, can you draw all of these? I don't expect you to know all of them, but I do expect you to know the ones that we discussed in class in great detail. So FCC, BCC, HCP to some extent, not the crystal planes or crystal direction. But basically what we've gotten in class and what your homework has, those are the types of practice problems that I do expect you to know and could do well on exam, say. Okay. Okay, so coordinates, check. Now let's do directions. Direction, this is a common methodology for determining the crystal direction. Well, first you have to pick an origin. As I've said, it can be arbitrary, right? So why not make it arbitrarily easy for yourself? The convention is if you see a unit cell like this where it looks basically cubic or maybe not cubic, right? The angles are not so well defined here and they don't look like 90 degrees, so why would we assume that it's cubic? But let's say you have some prism like this. If you make your life easy, you can pick the origin as being back here. That's pretty much by convention with, via right-hand rule. And this is something you've seen over and over again in, your calc class and your physics class. So just go by convention. And then you move in the direction of here by convention. This is x, this is y, this is z. And you move in the fractional form, okay? So how much do you move along this unit vector versus the y unit vector versus the z unit vector? And then once you've traveled that far, as denoted by what someone's telling you or whatever's on the page, then you draw and label that point. So here's an example of 1, 1, 1 in the red arrow. So I'll change the colors, right? So if you move 1 in x, so that's unit vector A, and you move 1 in B, so these are also A, B, C, and you move 1, so 1 in A, 1 in B, and 1 in C gets you to this point, okay? I've obviously exaggerated it so you can see very clearly back there. So if you're there, now you draw a line from the point you started at. So if we started at the origin, then you draw it there, and that's the head. Okay, from the tail to the head, and that's it. Okay, so I'm going to erase all my inner thoughts so it's very clear what direction we're talking about. Okay, and so the red marking should be what remains. Pretty simple. You probably have seen this and done this so many times when you're navigating through, in your calc class or physics or something like that. Now, when we talk about direction, we're talking about the way we denote that is with these square brackets. Now, let's say your material has some symmetry where it doesn't matter if you're trying to tell me that conduction is along the 1, 1, 1 direction or the bar 1, bar 1, bar 1. So let's say it doesn't matter if I'm trying to look at the unit cell this way or this way. Let's say it's anti-parallel, okay? So I'm going to change the color. I have red, green, and blue as my options. Okay, so you're just going to have to follow what I'm saying. So let's say, it's anti-parallel and it's going this way. So if it's 1 bar, 1 bar, 1 bar. So instead of -1, -1, -1, it's bar 1, bar 1, bar 1. That's the convention. So if you're trying to tell me, well, it doesn't really matter, they're all equivalent because that's just the symmetry of my material, then you could denote to another material scientist that the set of directions or the family of directions that I'm talking about is just 1, 1, 1. Yes?
So you think bar 1 indicates
It indicates it's what? No, it indicates the bar is a negative. Well, bar 1, bar 1, bar 1 is anti-parallel to 1, 1, 1. Yeah, but the bar is just negative. So could I have bar 1, 1, 1 in certain crystals? Yes, right? That could be the same just based on symmetry. So another example I'll give is another reference point. Let me just clear this up so you don't get confused. Let's say you go along, let's assume this is a crystal system, and you go along 1, 0, 0. So you went 1 in the A direction, 0 in the B direction or in the Y direction, and then 0 in the Z direction, okay? Well, who's to say that if I stand 90 degrees for a cubic system that it's not equivalent to this, or it's not equivalent to this, right? This is 0, 1, 0. This is, could be, if you're going, let's say, this way. If it's cubic, it shouldn't matter, right? It's all the same. The lengths are the same. A is equal to B is equal to C. It shouldn't be any different. So if you want to express that, you can just write something like this. Is that the same? You know, something like this. It's communicating to me that you have symmetry where it doesn't matter if you go in whichever direction. You've moved 1 unit length, or just 1, or whatever your unit cell is. You've moved 1 in that direction and none in the other directions, and all the x, y, z directions are equivalent, which is the case for cubic system. Okay? So that's why we have 2 different types of notations. One is just, if you really are trying to tell me, go in the 1, 1, 1 direction, I should not be going in the bar 1, bar 1, bar 1 direction, then just give me the square bracket, right? But if you're trying to tell me the material's property is equivalent and you want to talk about the set of directions, then you would use the angle bracket. So that way we don't have to keep on saying the set of directions. If I just write the angle bracket or the caret bracket, if I just write that, it automatically signals to you as another material scientist that I'm talking about the set of directions. It cuts down on the prose. Okay. Questions on that? Okay. So here's an example that if you see a direction given like this, let's say the green arrow is what you're given, you can see we're not starting at 0, 0. That's not the tail of the direction. Your origin is still here, but the tail of this arrow is here and the head is here. Okay. So if you use this common methodology called the head-tail method, you do exactly that. So 1, your origin is already denoted as O here. So your origin is already 0, 0, 0. Okay? So then the head coordinate is, well, let's take a look at that. You've gone 0 in A. Okay, I'm going to draw red just so I can write it over it and you could see it more clearly. So you've gone 0 in A, in X. Okay, and then 1 along this way. So you're here now, and then you've gone half up. Okay, so we end up at the head here. I'm going to erase everything. So that's how we get to the head. Where is the tail? The tail, you've gone 1 in this direction, 0 in Y, and 0 in Z. So that's how we get A, 0B, 0C. Okay. So that's your tail right there. So the difference is just going to be x2 minus x1, y2 minus y1, z2 minus z1. And so here's your tail, the x1. Here's the head of that direction. And so the difference is just -1, 1.5. At this point, you would not write this. This is not the convention. The convention is to always express it in terms of integers. So the example before was pretty easy, right? Ones and zeros. But here, now you're dealing with fractions, so you have to convert everything into integers. So the easiest way to do that is just to multiply all the numbers by 2. And this is what you would write by convention to express what is the direction, the crystal direction of this arrow that you see, or this direction that you see pictorially. This is how you would denote that. So you can see we've operated fractionally within the unit cell, but we communicate via integers. Questions? Yes, Bridget. Allison, sorry. Okay, so the question is, why do we go from the origin, or why was the tail origin, and now the tail is not? So that example is just because that's how the arrows were drawn. You know, could I have shifted 1, 1, 1 into, let's say, the next unit cell, like something like, you know, something like this? Could you have shifted that? Yes. And if I still called the origin here, let's say, if I still did that, but let's say this is shifted to, okay, now you're testing my 3D rendering abilities. Okay, let's pick something easy, like 100. If I had shifted this to, let's say, the 110, let's make it a little bit easier to see. Okay, one moment. If I had shifted it like this, this is equivalent to this, right? Even if I still told you the origin is here, you'll notice once you shift everything and you do the fractional, you know, you multiply the integers, you'll see that it's all the same. It's mathematically symmetric. Yeah. So we started there because the tail just happens to be there, and so math was easier for this example because you're just subtracting by 0. Okay. Now, let's do, okay, if you had to draw, let's say, 1 bar 1 0. This is a particular example. Yes. This one. Yeah. So right now I haven't said anything about the equivalency of the system. Right, I haven't told you that this is a cubic system, so you wouldn't necessarily know that there are certain symmetries that you could rely on. Right now, the head-tail method is just operating on the fractions of the unit cell. So if I went, all I'm saying when I say x1 equals a is that I moved one unit vector along the x direction, and that's length a. I didn't tell you what a is, and I didn't tell you if a is equal to b. I mean, a is here, it looks equal to b, but there is no precise declaration of that.
So are x, y, and z scaled by a, b, and c?
Mm-hmm. Yeah.
So then wouldn't any, regardless of the shape of the unit cell, we be talking like from 0 to 1 is going cell?
Yeah.
Regardless of if it was a cube or not?
Yes, absolutely. And so this methodology does just that. But I haven't said anything about the symmetry. When you say equivalent, when you say, okay, I'm going to use the angle bracket notation to talk about the set, I'm saying something about the equivalency of those directions. Let's say your material property, let's say you have FCC and you're going along the 1, 1, 1 direction. You're going from a corner, going through, or let's say maybe a better, okay, sorry, BCC. Let's say you start at a corner, 1, 1, 1, you go through the center atom, you hit the other corner. Who's to say if I start from the other side and I go in a direction, in the opposite direction, that I wouldn't experience the same materials property, like conduction or strength or whatever materials property I'm measuring, in which case that is equivalent. But this system, there's nothing to say yet that bar 2, 2, 1 is equivalent to 2 bar 2, 1. Not yet. Okay, so this system I've drawn, it looks eerily like cubic, but we don't have to assume that. It's the easiest to render. Okay, so if you had to draw 1 bar 1, 0, the specific example is if you see a bar like in a particular direction, it's advisable that you move your origin off of that corner. What do I mean by that? If your origin by convention is this back corner here, if that was your 0, 0, 0, you have two options. And I've seen it presented both ways, and they're equivalent. The first way is just to go with it. If that's your origin, then you would move. Let's define some of our directions here. If that's the case, then you would go 1 this way, -1 this way, and then 0 along z, okay? If that's your origin, in which case, then your arrow would look something like this. And if you had 3 unit cells like that, great, you're done. Now, let's say you're confined, and the question asks you, you have to draw this arrow within the unit cell that you're given. So let's say these don't exist, and you're just given the unit cell in the middle, and you have to stay in the middle. How would you draw that? Well, you could just graphically look at it and say, well, it could be like that, and that's the same, yes. Or mathematically, or the methodology that you could do, and this is one of the tutorials within Wiley Plus, is you can also just shift your origin over to here. Let's say this is your new origin. I'm going to call that O prime. Okay, so now the red, so now that's going to be Z, that's going to be X, and that's going to be Y. Same, okay? So if you shift everything now you deal with drawing this direction with your new origin. So you just shifted it 1 unit cell over. And so I'm going to choose green now. So you can go 1 in X. So that's 1 in X right here. And then bar 1 in Y. So you're over here at this point. And then 0 in Z. So that gets us to that. Okay? So, to recap, stick with your origin, fine. It should be equivalent, right? Your answer should not have been something like this. Those two are not obviously equivalent, right? That's a dramatic example. The second methodology is if you see a bar above a number, move your origin in that direction. What if you see it in 2 numbers? Move it in both directions. Move it. What if you see it in 3, like bar 1, bar 1, bar 1? Move it in all 3 directions. Okay? So let's do an example of that. So what if you had bar 1, bar 1, bar 1? How would you do that? So let's say we shift it. Let's say you do something like this. All right? So I shift it here, Y and Z. So now this is my new origin. So then if I move bar 1 in X, bar 1 in Y, sorry, oops, X was this way. X is now, sorry, X is coming out of the page, and bar 1 for Y is this way, and then you should be moving, oops, okay, bar 1 is this way. Oof, let's get our naming convention right. Sorry, folks. So if you move this way, and this way, you should get something that looks like going through the body diagonal from this corner over to here. Okay? 3D rendering is not my forte, but that's okay. We all have weaknesses. Okay, any questions on that? What happens when you move an origin? Why would you move an origin to stay within the unit cell? Questions? I did see a hand over here, and then I think it went down. You still got time to ask. Yes?
So between the
Yeah.
the numbers range from what to what? What's the interval?
Unit. 0 to 1. 0 to 1.
But already
Sorry. In terms of moving, but in terms of the notation, they're just integers. So in theory, you could have something, I mean, you can have any integer depending on the symmetry of your system.
so if we have like 11, 12, and 13.
Yeah, I mean, if you had some like crazy low symmetry structure that was triclinic, sure. Arbitrarily you could. I can't think of a system where we often deal with 11, 12, something. Typically what we're talking about are high symmetry directions. So that's why you see nice numbers like 2, 2, 1, 1, 1, 1, 1, 0, 0. It's because in real systems, the materials property usually propagate along those directions, like slip planes, conduction, conductivity, whatever. It's usually along some high symmetry. But that's not to say there isn't a special case where you could have 12, 11. I mean, that's really, honestly, out there in the sense that that would be unusual. But I can see where your concern would be, well, could you just have that on an exam where I ask you to draw 11, 12, 3? I mean,
How would the next person read it if they put one number next to the other?
yeah, I mean, in that case, right, you have, depending, okay, well, the exam is a whole nother, like the format of the exam is a whole nother thing, but really, you're a human being and we all have some limited vision, so I would not ever ask you to draw something so particular, you know, unless to get the point across that it's in some inverse direction, like a bar one direction or something like that. The point is for you to understand the methodology. I don't really want to, you know, give you an exam where I expect you to draw 1/12 of something. That's really not what I'm trying to get at. Okay, so if that eases your fear of, do I need to be as precise as 1/12 of something, the answer is going to be no. Okay. Yeah.
It's like a lattice or slanted.
Mm-hmm.
This
Yeah.
unit system, and like unity is the diagonal, or is it
No.
X, Y?
Yeah. It's just along the unit vectors. So if you had in your example something rhombohedral, it looks something like this, but it just has a different angle. It's slanted from cubic or something like that, right? It's offset. Yeah, you just go along A1 or X, Y, Z. So no, so so to answer your question, if you had something that looked like this, that didn't look exactly cubic, right? We still went along the edge. It's not now, yeah, you're probably thinking of projections back to a Cartesian coordinate or something, right? Where X, Y, Z is always orthogonal to each other. Eh. Yes, square bracket is just the direction, just a direction. So if you tell me 001, I've moved 1 along Z by convention of X, Y, Z right-hand rule, right? Z is pointing up. If you want to say a set of directions, like 001 is the same as 100, is the same as 010, you do angle bracket. If you're just trying to say, I'm just trying to move in the 001 direction, you're not saying anything else about 010 or 100, right? It's irrelevant to our discussion, just use your square bracket. That's it. Okay, let's go with, I have many examples, so you can work out some of those examples at home. Now, I want to move on to crystallographic planes before we hit linear density and planar density. So, the way we determine the indices, or the Miller indices, here it's HKL in parentheses, not in square bracket, not in angle bracket, parentheses, okay? the way we talk about the planes, right? So when we were talking about like, oh, the atoms that are at the face, or the atoms that are along a certain direction, well, there's could be a plane of them. So now we have to talk about the atoms on that plane. So before when we were talking about FCC, and I said, oh, look at the atoms at the corner and look at the atoms at the faces, I could have also just told you, look at the 100 plane. It would have been equivalent in terms of description, except one I used the Miller indices and the other I just verbally told you where the atoms are. So that's another conventional system, is how do we define the planes of atoms? So you have this whole list. You still have to select your origin. You read off your intercepts. You take reciprocals, and then you normalize the reciprocals to get integers, and then you reduce to the smallest integer possible, and then you put it in parentheses. So it's a little bit more involved in terms of the steps, but honestly, the convention is the same in terms of the way you view your unit cell. It's just more steps to think about is all. So I think it's best just to do a few examples together, and I think you're going to get the hang of it. All right, so first, relocate your origin. Here, we don't have to relocate it. It looks fine. There's nothing wrong with it. When you have to move your origin is when, by the conventional origin, which is 0, 0, 0. When you have to move it, it's because, once again, your plane is intersecting that origin, so you have to move it off in the direction, along the direction that it's intersecting 0, 0, 0. Here we see this blue plane. It's not intersecting 0, 0, 0, so we don't have to move it. It is not needed, as seen here. So let's look at the intercepts. Where does the plane intercept x, y, and z? So here in x, you could see if you elongate this plane, it crosses x at a, some distance a. So you can see here, we go out in a. So that's how they get this a. And then for y, it intercepts it right here where I'm marking. And that's b, or 1b. Okay. Where does it intercept the z direction, or the z-axis? It doesn't. So basically, the notation is infinity c, because it will never actually intersect the z-axis. Okay? So then when you take a reciprocal of that, you just put 1 over a. That's how you get 1 over a. Then you put 1 over b, where it intercepts. And then you see here, reciprocal is 1 over infinity c. And then you normalize it, and you say, okay, well, if I divide this by a, how many a's are there? Well, there's 1a, 1b, and 1 over infinity is 0. And thus, when you reduce everything, in this particular case, because it's all 1s and 0s, when you reduce it, it just becomes 1, 1, 0. And so the Miller index, the HKL notation, is just 1, 0, 0 with parentheses. So when you see parentheses, you're telling me I'm talking about a plane. I'm not talking about direction. I'm talking about a plane. So you're telling me all the atoms that happen to lie on this plane are the atoms on the 100 plane. Yeah, whole numbers. That's how we talk to each other. So this is an easy example. Well, in the sense that it's just 1s and 0s. So let's do something that looks a little bit funkier. Once again, should we relocate the origin? If we pick the origin to be here by convention, no, this plane does not intersect 0, 0, 0. We don't have to move your origin in any way. So where does the plane intercept x? Well, it didn't before, it intercepted over here, right? But for this particular case, it intercepts at halfway. Now, I eyeballed it, and it looks halfway. Now, on an exam, right, or your homework, either you're given something that's very easy and very straightforward, like a half, where you can see that, or if it's a quarter, right, we would put in markings so you could see, it's a quarter along X, a quarter of the unit cell along X, so that you don't have to guess, is it a quarter, is it a third, is it some funky number, is it like a 6 that I just arbitrarily chose? No, it will be very obvious, okay? So in this example, I didn't put any markings because it looks like a half. Also, I wrote half on there, so, you know, it doesn't throw you off. Okay, so along the y axis, you move 1b, and then it doesn't intersect c again, so we write it as infinity to express that it does not intersect c, the z-axis. And the reciprocals of that would be 1 over 1/2 is 2, so that's how we get 2a. 1 over 1 is 1, so 1 of b, and then 1 over infinity, we write it as that, which then, when you reduce everything, it comes down to 2, 1, 0, and so we call this the HKL, the 2, 1, 0 plane. That's how you would say it. Yes? How come the A and B don't end up in the denominator?
Why does the 1/2 a not become 2 over a?
Oh, yeah. So it should have been, because the A's and the B's, should have canceled out. I think this is clerical. Sorry. Thank you for catching my error. Okay. More. Here's another example. But you don't have to move the origin. So let me see if there's an example where, if I include an example where, here, let's do this example where you have to move the origin, or it would be advisable for you to move the origin so that it's just easier to work with. So here you could see if we were to work with this plane right here, you could see that it does intersect 0, 0, 0 at some point, okay? So let's move the origin along that direction, along the C direction. So if we relocate it to 0, 0, 1, so now I'm going to erase this and choose green. So now this is our origin, and I call that O prime for new origin. Now we can think about where does it intercept the new origin. Well, here it intercepts at, if this is x, y, z, it intercepts it at 1x, okay? And then for y, it intercepts at also 1, length of b, so that's a, b. And then if this is your new origin, it intercepts here, which is negative 1, c, okay? So this is negative 1c. So then when we take reciprocals, 1 divided by 1 is just 1, 1 divided by 1 is 1, 1 divided by negative 1 is negative 1, okay? So then when you reduce it, okay, there should be a negative here, so sorry for the second clerical mistake. So it's 1, 1, bar 1, so then you can write that this plane is 1, 1, bar 1 plane. So the HKL is denoted as so. Yes, question in the back. 1, 0, 0. If you want to move it here, 1, 0, you could, but now your plane is intersecting. You could see here it's intersecting your new origin. And you just moved the origin, so it wouldn't intersect your origin. Now, if you can't, just a side note before I get to you, if you kept your origin here, and you see, okay, if I continue this plane right here, and I keep going, where will it intercept z? It will intercept it at, negative 1. So that's another way of saying it, or another way of visualizing it if you don't move your origin. Question?
So is the best way of moving our origin to a point where
The bar is.
intersect?
Yeah. Okay. Let's talk about linear densities. Now, we talked about atomic packing fraction. We talked about ionic packing fraction. Now we're going to talk about the density, or that fraction, along a certain direction. And also, you can say the same thing about along a certain plane. So let's think about a linear density along a particular direction. One example could be the 1, direction in BCC. So now we are actually talking about a cubic system. We're talking about a material with some symmetry. This symmetry happens to be body-centered cubic. So the general approach is to count the number of equivalent atoms along that direction divided by the length of that direction in the unit cell, and that is your fraction. And why we would care about these numbers is it's helpful to know how atoms packed along each direction, to say, well, if the atoms are packed less densely in one direction than the other, that gives you a clue as to where the preferred, let's say, deformation is going to occur, which direction. And you can predict, if you have a certain material, the orientation, you know exactly how something's going to shear or whatever. Yeah. So it all relates back to the material's property. So how do we get to 2 over 4r as the linear density of 1, 1, 1? And so what you'll see is a notation like that. You'll also see linear density 1, 1, 1. So if we count the number of atoms centered along this direction, as you recall, it looks like 4r, right? This is the 1, 1, 1 direction in BCC. It cuts through the center atom. And so when you draw it, it looks like this. Okay? It looks like that. Which means it looks like there are 2 atoms. It looks like there's an equivalent of 2 atoms along this direction. So that's how we get the number 2. And the length is 1r, 2r, and another r for 4r. So the number of equivalent atoms in this direction within the unit cell is 2, and it's along 4r, or 4 atomic radii. It's all equivalent. So if you move it here, then it's there. So equivalently, to answer your question, mathematically, if you kept it here and you went to this, let's say you start here and you ended here, equivalent, right? Because of crystal symmetry, because it's cubic, it's equivalent in all directions. So you would have arrived at the same answer. The 2 atoms in the numerator is the 2 that you're talking about. The 2, linear is 1D, okay? So that means, well, in a 3D system, because I just gave you 1, 1, 1. But just look at the red line, this red line, or in your case, the other red line, it's all equivalent. If I started here, I pass through 1, 2, 3, 4. Those are the atoms I pass through, right? So if I project it on here, I draw it like this, 1r. I pass through a whole body center, so I pass through a whole atom, that's big, this big thing. And then I pass through another 1/8 of an atom, and that looks like that. But linearly, it just looks like I have 2 equivalent atoms, 1, and then 2 halves. But that's along the 1D, right? I'm just projecting on the 1D. I'm not talking about 1/8 of a fraction. That was the volume. So that's how I got 2. It looks like the equivalent of 2 atoms. Now, we can apply, so if we stuck in a real number, if we look in Appendix F or some periodic table, and we're given the atomic radius of a certain element, let's say iron. In this case, you see, okay, the atomic radius of iron is 0.124 nanometers. So this is the fraction. or sorry, it's that's the number, and the units are reciprocal distance. So here it's reciprocal nanometers. Okay, there are plenty of examples. So I didn't go through the other example, 111. Oh, sorry, that's planar density. There are other example practices in later slides. I would like to cover planar density next. So in the same way, you can have linear density. Now we're going to talk about the plane. If you happen to have a 111 plane in FCC, or a 100 plane in FCC, or 100 plane in simple cubic, whatever symmetry you have, you can also calculate how dense is it along the direction or in the plane. So here we can work out, let's see, oh, I've also rendered some, the plane, what planes look like, so that you can do your counting for simple cubic, body-centered cubic, as well as face-centered cubic. So let's see, what is a good example to do? Let me see, what do I want to talk about? We can talk about planar density in 111. Sure, why not? The planar density, the plane looks like this. Your 111 plane intersects the atoms and looks like this. Now, if you have a hard time visualizing this, I would suggest you open up your Vesta file. Your FCC iron will have the planes cut in. There's some files within the box directory that says 111 plane. Open that up, and you should see a rendering like this, so that you could see how the atoms cut through. And I would switch it over, except the switching takes a little bit of time, so I want to conserve time for today. But anyway, it's there. Visualize it. Play with Vesta. So the planar density is defined the same way. The number of atoms, but now it's on a plane. So how many atoms are on this plane within the unit cell? And then what is that area? And that's it. Okay, so before we had atoms divided by length. Now it's atoms divided by area, because it's a plane. So the area of this triangle is just 1/2 base times height. So you can work out the trigonometry here, right? So if your base looks like this, this is your base, this is your face, and this is your height. You can work out the relationship between the height and the base through trigonometry. But what I'd like to focus on before we leave is the counting, and we can revisit this, at the end, at the beginning of next lecture. But how do you count the number of atoms within the triangle? So in this 2D, so forget what we talked about in terms of 3D. In this 2D rendering, right, you have 1, 2, 3 halves in the triangle, or half circles. And then you also have 1, 2, 3, and that's 1/6 of a circle. Okay, we're talking about 2D now, so just take a look. Okay. So that gives you 3 halves of an atom, and that gives you 1/2 of an atom. You add it all together, you get 2 atoms. That's how we get to that. Clear? Now, think about the 2D, okay? Look at the triangle and just count the area fraction. And that's how you get to the number of atoms on the 111 plane. All right, with that, have a good weekend.
So our rest taking instructor said that exams are on common, but on the syllabus it